Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to have here again Corina Passariano. She already gave a talk on Thursday about testing with symbolic execution Java Pathfinder, and now we're going to hear about automated assume guarantee reasoning.
Okay, thank you for the introduction, and thanks again for having me here. So today I'll talk about different techniques that we have developed at NASA Ames for automated compositional verification that use assume guarantee reasoning. And this is joint work with my colleague Dimitra Giannakopoulou. And over the years we had many collaborators, so I listed some of them here. Professor Howard Barringer, and also summer students Jamie Cobley, Mike Hemi, and Mihaela Georgiou. And in fact, I visited here 5 years ago together with Dimitra, and we presented our initial framework for automated assume guarantee reasoning here. And in this talk, I'll revise a bit that framework, and then I'll present our subsequent work, how we extended, and how also the alternatives that we have investigated. So the context of this work was a project that investigated an integrated environment that supports software development and verification and validation throughout the software development life cycle. And the goal of our work was to detect integration problems early, prior to coding, basically at the model or design level. And so the idea is that one starts with some requirements, maybe written in English, then it builds these, one builds designs, which are some formal models of the software, which are then translated into source code, maybe automatically by code generation or not. And then this follows with testing and, of course, deployment. So our techniques address design models when it's, of course, easier to detect and fix errors. And we also did some work on using the artifacts of verification at design level to check the actual source code. And in particular, we investigated compositional, meaning divide and conquer techniques for verification to increase scalability. So what is the problem that we addressed? It's compositional verification. So assume we have a system composed of many modules, M1 and M2. Let's say M2 is composed itself by many other modules. And we also have a property. In our context, this is a safety property that specifies the desired behavior of the system. And we want to check if the system made up of M1 and M2 satisfy the property. So checking property P on the entire system may be infeasible because there may be simply too many states to examine. So the idea is to use the natural decomposition of the system into its components to break up the verification task. So we want to check each component in isolation and hopefully infer something about the whole system, the integrated system. So we want to check if M1 satisfies P. However, because our property P refers to the interaction between different models, typically it doesn't hold on M1 itself. So you usually need some form of abstraction about the rest of the system to be able to reason about a component M1 in isolation. So this is what assumed guarantee reasoning is doing. It introduces assumptions A representing M1's context, operational context. And the idea is that A abstracts away the internals of M2 and just keeps enough information about the interface interaction between M1 and M2. So in assumed guarantee reasoning, which was introduced a long time ago, and I'll give a bit of background information in the end. One reason is about assumed guarantee triples of the form A and P. And this formula is true if whenever M is part of a system that satisfies A, then the system must also guarantee property P. And here again, P is a safety property. So the simplest assumed guarantee rule that I'll call asym, because it's asymmetric, you'll see later some symmetric rules, first checks if M1 satisfies P in the context that satisfies A. And of course, to complete the reasoning, one needs to discharge A on M2. And if these two premises hold, then we can conclude that M1 together with M2 satisfies P. So using this rule, you can check the composition of M1 parallel M2 without actually building the product of the state spaces of M1 and M2, but rather reasoning in isolation about M1 and M2. So how do we come up with the assumption A in order to reason about such properties? This is basically the problem that we address here. And I'll present several solutions. And one is to use a learning algorithm to come up with A in an iterative fashion. So this is the outline of my talk. First, I'll present a framework for learning-based assumed guarantee reasoning, and we introduced it in a paper a long time ago at TACAS, and this is what also I presented here with Dimitra 5 years ago. And then I'll present extensions of this framework with different symmetric and circular rules, and an extension that looks at refining the interface alphabet between components with the goal of making the verification even more tractable. I'll talk about implementation and experiments and different other extensions. And also I'll present a bit an alternative to this learning approach that we have explored recently, and it is based on the classic Seeger loop on building abstractions of the other components. And we called it AGAR, and we had a paper on that at CAV. And finally, I'll talk about related work and conclusions. So first, a bit of formalisms. So in our work, components are modeled as finite state machines, and they are assembled with a classical parallel compositional operator that basically synchronizes on shared actions and interleaves the remaining actions. And the safety property is yet another finite state machine that describes the legal behaviors of the system, or alternatively, the complement of P describes the undesired behaviors of a system. And then we say that component M satisfies P if the error state, so P error is the complement of P, which is achieved by determinizing and completing P with an error state. And then M satisfies P if the error state is unreachable in the composition of M with this P error. And then assumed guarantee reasoning in our framework reduces to checking. So if we want to check a triple of the form A and P, we check that the error state is unreachable in the composition of A together with M together with P error. So this is our formalism. Other people looked at other kinds of finite state formalisms and applied similar techniques, and I'll talk more about that. And as a simple example, let's consider an input, a system that has two components, and an input and an output component. And the idea is that a message comes in, then it's sent to the output component, and it waits for an acknowledgement to be received. So when we put these two components together, input and output, the highlighted actions, send and act, will be synchronized, while in and out, which are local to input and output respectively, will be interleaved. And then this is an example of a property which specifies that messages come in this in-out order. Is again a simple automaton. The gray states are the initial states, and the order error, meaning the complement of this automaton, is achieved by completing it with an error state, the red one, and of course completing with the remaining transitions. So now what do we do with learning for assumed guarantee reasoning? As I said, the idea is to come up with assumptions A such that the premises of rule asym are satisfied, or if in case that the composition of M1 with M2 doesn't satisfy the property, to output an error. So we use an off-the-shelf learning algorithm to build appropriate assumptions. The process is iterative, and the assumptions are generated by querying the system, and they are gradually refined based on counterexamples obtained from checking the two components separately. And the termination is guaranteed. So we are actually in a finite state world. Everything is finite state, so we are safe here. And in particular for learning, we used the L-star algorithm that was developed by Anglin and later improved by Rivest and Shapiri. And this algorithm learns an unknown regular language U over some alphabet sigma and produces a deterministic finite state automaton A such that the language of this automaton equals the unknown language U. And in order to do that, L-star needs a teacher to answer two types of questions. And one is queries, and the other one is conjectures. So for a query, L-star asks the teacher if a string S is in the language or not. And the teacher needs to accurately answer yes or no. And based on this information, L-star adjusts its internal structures in order to discover the language. And after many queries, L-star is ready at some point to make a conjecture, meaning to make a guess that based on the information it received so far, it builds an automaton AI, and then it asks the teacher if the language of AI is equal to the unknown language U. And if this is false, meaning T is either in the language but not in the unknown one, and vice versa, then this counterexample is returned to the L-star, which again adjusts its data structures so that to encode this language, this knowledge. And if this is true, then we are done. Basically, we discovered an automaton whose language is equal to our goal, the unknown language U. So now, how do we use this L-star algorithm for our purposes? As you may have guessed, we use L-star to learn the languages of our assumptions. So, as I said, our goal is to come up with an assumption that satisfies premise 1 and 2 of this rule. So we fix the alphabet of our assumption to be basically the alphabet of the interface between the composition of M1 with P and M2, and we can talk more about that. And the idea is that we also need to come up with a teacher for this language, and we implemented the teacher using model checking. So how does this work? As I said, the teacher, basically our contribution is how to implement this teacher using model checking for the purpose of solving this equation, this system of two equations, the two premises of our assumed guarantee rule. So when L star asks a query, basically we are interested in finding out if string S is in the language of the assumption. And what we do is basically we try first to come up with an assumption that satisfies the first premise of the rule. So basically we check if in the context of this string M1 satisfies the property or not. And if it does, then it means S is good. It should be part of the language of our target assumption. And if not, we say no, and L star will adjust its language. And basically this is like a simulation of S on the composition of M1 with the error automaton for the property. Now, as I said, at some point L star, after many queries, is ready to make a conjecture. So it made a guess for an assumption AI. So now we are ready to check the two premises of the rule. If both premises hold, so we check this with model checking, then we are done. Basically, since the rule that we use is sound, it is safe to say that we found an assumption A such that P holds on the whole system. Now, if in the context of this assumption M1 that violates P, this means that the learner needs to do more work to come up with an assumption that at least satisfies the first rule. So we return the counter example after we project it on the interface alphabet so that L star can keep refining the assumption. Now, if the second premise is violated, then there are two causes for it. Maybe we discovered the real error, so it just happened that M1 together with M2 simply cannot satisfy P. And then we need to report this to the user that we found an error. Or it may be the case that, again, A was not good enough. So we need to return the counter example to L star, and L star will do more work and adjust the assumption, and the whole process will be repeated. So basically, we do here a bit of counter example analysis to see which case is, what is the case here. And either we return that P is violated or we need to do more refinement. And the counter-example analysis basically takes the trace from the check of the second premise and it tries to play it back on the first component, in some sense to discover a trace that is common to the composition of M1 and M2 without actually building this composition. And this is the idea. And then I put here a bit of characteristics of L star and how we use it. So our framework terminates with a minimal deterministic automaton for the language U. And it also has an interesting property that it generates candidates with increased size. So this is good for verification because it increases the chances of finding the small assumption that is necessary to check the two premises of the rule. And then I put some information about the runtime of the L star algorithm. So again, going back to our little example with the input-output components and the order property, this would be the computed assumption that our L star based framework will generate. And this would happen after 2 iterations, so after 2 refinements of the conjectured automaton.
Which is M1? Input is M1 and order is M2?
Input was M1 and output is M2 and order is the property. So, but in fact, we always look at the composition of M1 and property together. So we decompose it in two. So now what I presented was basically how one can reason about a system composed of two modules. But in fact, we extended our work to reasoning about more than two components. And this is done in the following way. So basically, in order, to check if M1 parallel M2 parallel Mn satisfies P, the idea is simply to decompose the system into M1 and the rest, and then to apply recursively our algorithm for the rest of the system. So basically, we apply, for the checking the second premise, basically we view A as a new safety property, and then you can again apply the same, basically create a new instance of the learning framework to solve this problem.
So, I have a question. So, generally, when now you have this set of n processes, there might be very interesting subsets, and you're choosing some sequence. It might be that you want to, choose Mi and Mj and Mk with some particular.
So at least, so of course, the advantage of this method is that now you will never compose components. So you'll always look at a component in isolation. But of course, the order in which you pick these components, so this is biased in some sense to which method you pick to be M1 and M2 and so on.
But it's also linear, and it might be very useful to subdivide, right? To consider some subset, compute the assumption for that subset.
It is. So, in fact, I'll talk a bit later, but a student of Rajiv Allur, who actually extended this framework for his PhD thesis, he looked at different decompositions for this, and he has a paper on that. I think it's a slippery ground there, so it's a bit hard to. The problem is not solved, how to come up with a good decomposition and the things. So I'll talk a bit more about that. So now we have further extended this framework to reason about other rules, and I just want to emphasize that.
Can you go back to the previous slide?
Yeah.
So I don't understand how you do the recursive call.
Yeah.
You have to first compute A before you can make the recursive call, right?
So here, basically, we localize. The L star in some sense focuses on finding a good A that satisfies the first premise. And then for the second premise, imagine that instead of M2, we have M2 parallel M3 parallel Mn. So here we create a new instance that will call recursively. It will create a new instance of the verification of the learning framework that will give M2, which is now a composition of other little modules, and now the current A will be the current safety property. And then when that one will return, so this new recursive invocation might again make recursive calls and so on until you reach the last module when you can just apply model checking. And the result will again be either that the property holds, in which case we will also say it holds, or a counterexample, and then it will go back. And this is how it works. Actually, all these algorithms have been implemented and we moved them into JPF, so they are publicly available. We can talk if you are interested to look at them.
So when you do this recursive invocation and the A on the top level changes, do you have to throw away all the things you found out so far?
Yeah, there are again other people who extended this work. You can of course reuse the tables, and so you can reuse much of the work. And people have looked at that to not completely throw away the information. It requires a bit of understanding of the internals of L star, and it keeps the information in a table, and then you can just recheck that table and remember it for subsequent invocations. So it was a good question. So I would just want to emphasize that using this idea, one can solve many such rules, assume guarantee rules. So I want to emphasize a bit let's say, the generality of this approach. And this is an example of symmetric rules. So the previous rule the first rule that we have studied was asymmetric in the sense that in some sense it was biased towards the first component. So we have investigated symmetric rules that come up with assumptions for both components at the same time. And this is an example that we describe in a paper that we have together with Howard, so Dimitra and Howard. And this rule says that if M1 satisfies P under an assumption A1 and M2 satisfies P under an assumption A2, and moreover the language of the complement of A1 parallel complement of A2 is in the language of P, then M1 parallel M2 also satisfies P. And we can talk more about this, but basically we show that this rule is sound and complete. And I'll just show you how we use the learning framework to automate it. You can imagine how to do that. And I should say that completeness is needed to guarantee termination, but we can also accommodate incomplete rules, but then you don't have this guarantee. But the rules should be sound, otherwise it will make sense. And there is, of course, a straightforward extension to n components, but then the problem is that so you would have n premises of the form AI, Mi satisfies P, but then the last premise will still compose all these complements of the assumptions together. And this could be expensive in general. Now, we have done some experiments and we found that this extension to n components is less efficient than the other one, the extension for the asymmetric rule. But other people, for example, Sagar Chaki, a student of Ed Clark, he also implemented a similar framework in his work, and he found that this rule is the most effective. So basically, you should use these rules as heuristics and try to decompose the problem, but there is no clear-cut solution to this problem. So this is how we automate the symmetric rule. Basically, now we create two L-star-based assume guarantee reasoning frameworks, and they can work in parallel, and each learning box tries to come up with an assumption AI for the component to satisfy the global property P. And once we have that done, we can apply the final check. And if it's true, then we can conclude that P holds in the composition. Otherwise, we need to do a counter-example analysis, which is similar to the one that we used for the asymmetric rule. And we conclude either that the property P is violated, or we need to refine the assumptions. And we have looked at also at a circular rule from proposed by Orna Grunberg in 91 in a paper at conquerGF. So this one, for example, looks at tries to come up with an assumption A1 such that M1 satisfies P, and then it discharges A1 on M2 under a second assumption A2, and then A2 is discharged back on M1, and then we can conclude that M1 parallel M2 satisfies P. And again, they prove that this is sound and complete for our framework. And it's very easy to automate. Basically, this is similar to the rule asym applied recursively to three components, where we simply fix the last component to be the same as the first one. And again, it has a straightforward extension to n components. And in the past, we have also looked at other rules that there are many rules in the literature that some of them involve induction over time. For example, we looked at a rule by Chandy and Misra from a paper in '81. And as I said, I want to emphasize that our learning framework is quite general, so it could accommodate many such rules. So now I'll talk a bit about extensions of our work, and I'll start with alphabet refinement. So this is some work that we did together with student Mihaela, and we presented last year at TACAS. So the idea is that in our basic framework, in order to automate the asymmetric rule, we fixed the assumption alphabet to be basically the intersection between the alphabet of M1 parallel P and M2. So this is basically the alphabet of the interface, communication interface between these two components. However, we observed in previous work that usually a much smaller interface alphabet is necessary to prove a property, because maybe the property doesn't even refer to some actions that participate in the communication. So we observed that with smaller alphabets that we build by hand, it is often sufficient to prove the desired property. And of course, a smaller alphabet would also lead to a smaller assumption. So basically in this work...
Can you give an example of this phenomenon?
Yeah, I'm not sure if I have the slides, but the idea is that, let's say, I remember in an experiment we looked at a client-server application and we wanted to check some mutual exclusion over a resource. But actually the server would mediate access to the resource and also offer other services to the client. So there was more communication between the client and the server that simply didn't matter for the property of mutual exclusion of a particular resource. You see what I mean? So the intuition is similar to slicing. So sometimes you have a property and you can forget about the other actions, so you can make the communication looser, because it's enough to forget about that information to prove the property. And so in this way you can obtain coarser abstractions, and of course this lead again to better verification problems. And I just described this briefly here, but all the details are in the paper. So we start with a small or the empty alphabet, or usually the alphabet of the property intersected with this interface alphabet is enough. So the idea is that the actions that are in the property usually are important. And then we try to slowly discover the rest of the actions that still help you to prove the property. And this is again discovered by analysis of counterexamples obtained from model checking. And as I said, all the details are in our Takasu 7 paper.
Actually, I have another question. Perhaps it's a question for later. But like when you analyze using your tool these client-server examples, there's probably lots of other CRUD that is sitting there in addition to the actual protocol that you wish to analyze.
Mm-hmm.
How do you extract the protocol from the program?
So okay. In particular, let's say you can apply slicing anyway beforehand, but actually our assumptions automatically extract only so in our framework, as I said, we fix the alphabet, or we try to discover it, but eventually we converge to the alphabet of the interface, of the communication interface between the components. So everything else, even if M2 does some very complicated calculations, but they are internal actions, they will not appear in the assumption. So our algorithms automatically abstract away the internal behavior. This is the idea. You want to look only at the interface behavior of the assumption.
So I guess the point is that I mean, this is a complicated infinite state program.
Everything is fine.
But not the client-server application, right? That's not finite state application.
I'll talk a bit about it. It's actually a component that Gerard analyzed with Spin, and we used it. So he abstracted away already the information. So
clarify, your starting point is the finite state abstraction of the real system.
Yeah,
Right.
so everything is finite, yeah. So, or we, like, as I said, you start with finite state models. And we did a bit of work and I'll talk a bit with CMU, with Ed Clark and Sagar, to apply predicate abstraction with his magic tool to extract finite state models from a C program. So you can devise a scheme to combine them, and we have a technical report on that. But for as far as this presentation, up to this point, everything is finite state. Okay. It's still very difficult, we find.
So just to make sure you understand the alphabet refinement. So when you say you start with a small empty alphabet, you mean you start with a subset of the original alphabet, of the true alphabet?
Yeah, in practice we start with the alphabet of the property. So the property is a global property, and we intersect it with the alphabet of what is common between M1 and M2, which we view as the interface, because this is the only way M1 and M2 can communicate.
Because I think I remember at one work where, so you start with an under-approximation of the communication alphabet and you add.
Yeah, this is
There's the other way where you start with a partition of all the.
Yeah, this is what Nishant did.
So that's different.
Yeah, it's also an extension of this work. I'll talk a bit about that. Yeah, so he tries to cluster. He has still a fixed alphabet, which is this one, and then he tries to cluster the communication alphabet. He has a different terminology, and he uses predicates, and he clusters them together. Again, hopefully that would be enough for what you get. Okay. So then I'll talk a bit about implementation and experiments. So we initially implemented everything in the LTSA tool, which is a tool developed at Imperial College. And LTSA stands for Label Transition System Analyzer. And we implemented the learning using the rules A, Sim, Sim, and Circular, with support for reasoning about 2 and n components, and also alphabet refinement for all these rules. Mihaela did that. And we performed several experiments that compare the effectiveness of different rules, and also they measure the effect of alphabet refinement, and more importantly, measure scalability as compared to non-compositional verification, because of course this should be the ultimate goal. So these are some of the case studies for which I found nice pictures. So one is a model of a K9 rover executive. We have now a K10, and the next generation is being developed. So this executive acts like an interpreter for plans that are written in a domain-specific language for commanding robots. And we analyzed a subsystem composed of an executive thread and an exec condition checker thread that monitors different state conditions. And we checked, for example, that a specific shared variable should be cleared. If the executive reads it, then the other component should not read it until the executive clears it. So this is just an example of the property. And this is the client-server application that I mentioned. So this is a resource arbiter developed at JPL that performs local management of resource contention between resource consumers, and consists of k user threads and one server thread. And we checked mutual exclusion between resources and other properties. And we started, for example, for this one with a Promela model that was also finite state that Gerard Holzmann developed, and then we translated it into the LTSA input language, and we applied our techniques.
I have a question.
Yeah.
Go back. I'm a little bit curious of your formulation of the example property. if I had to formulate these kinds of properties, I would just have formulated them as assertions. But this has some temporal nature to it. Was this very important? Was this very needed? Could you not formulate them as simple assertions without talking about the history of the computation?
In LTSA, I forgot exactly. I think we had again just a simple automaton for this property, and you can in LTSA you can also have LTL properties that use some fluents, and then they are translated automatically into safety automatas if that is the case. But it doesn't matter. Other people, and I'll talk about it. You can have assertions. This is not important. The main important thing is, at least for our work, that they are safety properties, but people extended this work to liveness, and I'll talk a bit about that. And what you really need to apply, in order to apply this technique, is a clear notion of components and also the interaction alphabet between them, so that you know how to start the learner. We can talk a bit more about that. So here are some results. In our case, we found that the asymmetric rule applied for n components is more effective than the symmetric and circular rules. But as I said, other people for a different set of experiments found that the symmetric rule is more effective. And then we found that the alphabet refinement improves learning for all the rules, and this is significant. On the other hand, this is by no means the solution to the state space explosion problem. So sometimes it doesn't work. Sometimes it can incur significant time penalties. It is not always better than non-compositional verification. So sometimes it's simply better just to apply verification to the whole composition. And but sometimes it's significantly better in terms of memory. And here are some results. So for example, for this MER case study, we applied it with increasing number of components. I should say that, for example, Gerard didn't believe in this technique, and he applied this spin to MER. But I think we convinced him, at least with this case study, that there is some merit to it. So at least for a case study that he understands, we were able to beat monolithic verification for 6 clients. And basically, okay, so what do I show here? This is the size of the assumption. And then this is memory and time. And this is the result of the application of the asymmetric rule. And this is together with alphabet refinement. And as you can see, for small systems, just checking the whole system is very fast, so it's not worth it to go through all the trouble of decomposing and coming up with assumptions. But as the number of users increases, then the results for compositional verification, especially with alphabet refinement, get better. And actually, for 6 users, LTSA was not able to check the whole system. And we also implemented this technique on top of the spin model checker, and also spin in a monolithic way was not able to go beyond this number of users. Now, as I said, the time overhead is pretty significant, and this is not surprising because there are a lot of iterations. So you have a lot of queries and iterations from the learner, and also with the alphabet refinement. So you start with a small set of actions and you keep adding it. So of course a good guess of this alphabet would help such techniques.
In these examples, they are symmetric examples, correct? So your technique, or assume guarantee verification of that type, critically depends on the decomposition, M1, M2, Mn, etc.
Yeah.
So, but here, the M's are symmetric processes. Is that true?
For MER, they are almost symmetric. So you have n identical clients, but one server. So usually this is bad for compositional verification.
And the the property itself is kind of doesn't distinguish these M's itself. Is that correct?
It does. So the property also increases with the number of N.
But there's one server and a bunch of clients. Is that correct? But then the property itself doesn't distinguish clients from each other.
No, I'm not sure. So, for example, yeah, maybe, yeah.
So the question is like, I mean, if the techniques critically depend on decomposition, M1, etc., did you try several decompositions?
We tried, yeah.
Or it doesn't matter because it's symmetric? And second question,
we didn't have too many choices. So we tried first the server and then all the clients, or we tried first the clients and the server, or in the middle, or something like that. So we tried not systematically. We tried for small systems, and we saw what works, basically.
And compared to like a straight model checking, does LTSA use symmetry reduction? Did you try with a model checker with symmetry reduction?
We tried with spin. So actually, because now if I remember, I think these results, I forgot, but I think they are with spin. I think spin has partial order reduction.
But not symmetry reduction.
Yeah.
But
the symmetry reduction, I'm not sure if it would help here. We didn't, but I agree.
The best, like a client server, it's the best scenario for symmetry reduction.
But then you can apply symmetry reduction also during our little decompositions. But we didn't. But you see what I mean.
But
so
symmetry reduction only works if it's exactly the same processes, and the properties, of course, agnostic. I mean, cannot distinguish the processes. If you have a little thing in your model that breaks that, symmetry reduction will not apply.
Yeah, but
But I'm just curious to see.
Yeah, we didn't try. We didn't try. Just as a comment for what, if it's worth it, is that of course you could apply all these techniques also on our little verification problems. But I understand it's a valid question. So we didn't. Yeah. Sorry.
These numbers represent the best decomposition orders that you could find?
I think actually for Murray it didn't matter that much, because as he says, we just took one, it didn't matter that much. I forgot, I think we kept the server the last one, and probably it was the best. So this is again a valid question. Maybe you don't have time to find the best decomposition. So you would need usually in real applications we found there is a natural decomposition. So you would know maybe this is the subsystem and they should be loosely coupled. Again, this is let's say the lesson that we can say, because the alphabet of the interaction matters for the size of the assumption. But there are some studies, and I'll just discuss a bit more systematic studies that other people did that hopefully would give more insight into that. So I'll just talk a bit about some other extensions that we did. So one was to apply this learning-based reasoning at the design level, and then assuming somebody wrote the code for the designs or used code generation to get code from the designs to use the assumptions and the properties to check the implementation. So essentially what our framework does, it decomposes the property, the global property P, into local properties that then you can use for other purposes. So you can use it, for example, for unit verification or unit testing of software components. And this is more or less what we describe in that paper. I already talked a bit about this extension of spin, and this is described in a paper that appeared at the Spin workshop in 2006. And we are working on porting our techniques in Java Pathfinder, and actually there is an extension in JPF which is called compositional, so it contains all our learning algorithms. And for now we provide compositional reasoning for UML state charts. So JPF, our tool at Ames, has an extension that allows one to model UML style state charts. And we are working, basically how we want to use these techniques is to do interface synthesis, similar to what Rajiv Allur did, for example, in a paper at Popl, I think in 2005. So the idea is to compute an interface or an assumption for M1 in the absence of M2. But of course, once we look at code, basically at Java, the problem becomes more complicated. So you need some form of abstraction to get finite state models. Also, the interface is no longer clear, so there is more work to be done there. So we looked a bit at compositional verification of C code, and this was done in collaboration with CMU. So basically, Sagar visited once our group, and he had this tool called Magic that would apply predicate abstraction to extract LTSs, label transition systems, from C components. And these LTSs would compose exactly, they looked more or less exactly like the LTSs that were used in our tools. So we integrated our work, and we have a technical report for that. And then we also have a recent paper that appeared at FM this year that applies this work to interface automata. So until now, in the formalisms that I presented, we did not distinguish between inputs and outputs. But of course, there are richer formalisms that distinguish between, for example, the send of a message and the receive of a message. And this distinction is quite subtle. So in some sense, you can control how to send a message, but you may just choose to respond or not to receiving it. So the semantics of composition becomes a bit more complicated. And in this framework, in this paper, we defined the rules for checking so-called compatibility between interface automata. And this helped uncover errors that couldn't be found just by checking safety properties on the formalism of LTSs, for example. And you can find more information from my webpage and also Dimitra's webpage. So just to summarize a bit, I listed here some of the possible applications of these assumptions. So one is support for compositional verification. Basically, as I said, these assumptions are used to automate assumed guarantee reasoning. And they can be also used for component documentation. So, as I said, from a system level global property, you can get local properties or contracts of your components and maybe ship them, view them as some sort of certificate of your components. And we are looking at interface synthesis. Other people also looked at that. They can also be used as software patches. So if you view your component as your software of interest, and let's say the component violates a property, you can build an assumption that together with your component will satisfy the property. So it would be like a patch that you apply to your component. And we did some experimentation with that. And they can be also used for runtime monitoring of the environment. So, for example, the assumptions that are obtained at design time maybe can be deployed together with the software and to act as guards and of the behavior of the software. And other applications include component retrieval, component adaptation, and so on. So I'll talk a bit about related approaches. So assumed guarantee reasoning has been introduced a long time ago by Jones and Punelli. I think they were called differently, assumption commitment paradigm, or I forgot the other two, maybe Shaz knows. And a lot of people have been looking at assumed guarantee frameworks, and early tool support for this kind of reasoning was provided by Mocha and also Calvin. Then we introduced this learning-based assumed guarantee reasoning, as I said, at TACAS 03. And since then, many other frameworks were developed that are similar in spirit, but they're different in the kind of model checking that is used and the kind of communication paradigm that is present between components. So, for example, Rajiv Allur and his students have a paper at CAV 05 and also an extension in 06. I forgot the paper, but they looked at, they came up with a symbolic BDD implementation of this L-star framework, and it is used for new SMV. And they also looked at hypergraph partitioning for model decomposition. So this would be a good pointer if you are interested in how different decompositions, to see how different decompositions affect verification. Then Natasha Sharigina and Tol looked at checking component compatibility after component updates. So here is a bit related to maybe your question. So the idea is you perform the verification in this assumed guarantee style, and then the component is updated or you replace it, and how to reuse the information from the previous verification to come up with new assumptions, to adjust previous results for these updates. Then Sagar, Chaki, again at CAV, I think, had a paper that checks simulation conformance rather than trace inclusion. So we defined our framework for trace inclusion, but he looked at simulation conformance, which is cheaper to check than trace inclusion. Then Nishant Sinha, who is another student of Ed Clark, did a SAT-based framework that uses lazy learning, and he proposes alphabet clustering and learning from sets of traces. And he had actually this as a topic for his PhD thesis. And then there are other people who did similar follow-on work. I know of this one, but I think there are many others. I know of a recent work that applied such techniques in the context of timed automata, for example. Somebody in Sweden. So then a related approach is the one by Rajiv Allur at Popl in 05, where he applies the L-star for interface synthesis. So the idea is to come up with an assumption for a component to satisfy the specification in the absence of the environment. So basically, he doesn't have the second oracle that we use. So he had to come up with different heuristics for the second oracle. And then at TACAS 07, there was some work that was developed independently from us by Sagar and Ofer Strickman. And they also looked at learning with alphabet refinement. But while we came up with some heuristics to grow the alphabet from interface alphabet from a small set to a bigger one, they formulated this as an optimization problem. So they tried out to come up with a minimal alphabet that is necessary to prove a property. And then there is another work by Ken Macmillan and some students at CAV 07, which looks at an alternative to L-star, which is based on a sampling approach and a SAT solving technique. And they also compare with our approach, and they find that this is better. And then there is, so as I said, our work was done in the context of safety properties, and it used this L-star algorithm that learns finite traces. So actually there was, and of course the question is how to use a similar framework for liveness properties. So there you would need to apply learning for infinite traces. And actually such an algorithm was lacking in the literature. So there was some work by Odette Mahler long time ago, but it was incomplete. And then Ed Clark and I think some postdoc students came up with a new algorithm that was presented at TACAS 08 that performs learning for infinitary regular sets. So the main contribution there, I think it's a general contribution that now there exists a L-star extension that learns automata for omega regular languages. And as a direct application, this can be used to automate assumed guarantee reasoning for checking liveness properties. And there may be more related approaches. And just quickly, I don't have too much time, but I just want to talk a bit about our Seeger approach, and in general Seeger for compositional verification. So Seeger is this paradigm, counterexample guided abstraction refinement, proposed by Clark or maybe Bob Kurshan before. And of course you have many tools here, the famous SLAM tool that performs Seeger. So the idea is that it builds conservative approximations of concrete systems, and counterexamples obtained from checking abstractions may be spurious, and they are used to refine the abstractions. So given a concrete system, one can build an abstraction, apply model checking. Based on the counterexample, they refine the abstraction. The result is either that the property holds or not. And previous work looked at using this framework for automating compositional verification. So for example, there is this work by Sagar that tries to analyze C1 para C2 para Cn to see if it satisfies P by first building finite state abstractions, A1, A2, An, minimizing them so they have a two-level abstraction, and then analyzing the composition of these abstractions and to refine them based on counterexamples. And also there is a lot of work by Tom Henziger that uses Seeger to compute interfaces, so that they are similar to assumptions. But just to tell you quickly, we have a result of that was presented at CAV a few weeks ago. So a question that actually Moshe Vardi put a long time ago was, okay, so when we look at this rule, A needs to be satisfied by M2. So you can view A as a conservative abstraction of M2. So why don't you just build A as an abstraction using, the theory of abstract interpretation, and then plug this A into the first premise. And this is basically what we try to do in this work. And also we try to see a bit how it compares with learning. So the idea is that we build A as an abstraction of M2. So we no longer need to check premise 2 automatically. It holds by construction. And then we just need to check premise 1. And the obtained counterexamples are analyzed and used to refine A. And we call this assumed guarantee abstraction refinement. It is a variant of Seeger with the following differences. So we use the counterexample from one component to refine the abstraction of the other component. And furthermore, A is a coarser abstraction than, let's say, the classic abstraction that you would build, because it keeps information only about the interface alphabet. So it has some closure operations that are involved in building these abstractions. And we implemented this in the LTSA tool, and also we combined it with the orthogonal approach to alphabet refinement. And we found that in general it compares favorably with learning, but it is not always the case. So I should say that this is expected, let's say, because in our learning approach, A was required to be deterministic, while here this is no longer necessary. And on the other hand, we need to perform more experiments to really see the merits of the different approaches. And also the point is that the extension of this approach to other rules is not that clear. So we thought about it, but it's harder, it's no longer possible to apply it in cases where, we don't have rules of this kind. So for the symmetric and circular rules, it's a bit more complicated. While the learning one, let's say, maybe it's easier or more elegant. So in conclusion, I talked about this learning-based assumed guarantee reasoning. It is general, it can automate many assumed guarantee rules, and it can use any model checker that can do simulation, and also it can provide counterexamples. Of course, it also needs a clear notion of components and their interfaces. And it is also applies to finite state machines, so you will need some abstraction if your systems are not finite. And we also investigated a bit an alternative to learning that performs abstraction refinement. And this is the current and future work. We are moving our techniques into JPF, the Ames verification tool. We are looking into assumptions with richer alphabets. For example, we are looking at interface methods that have parameters, and then the alphabet is no longer just a symbol, but maybe a symbol annotated with some predicates. We want to look beyond safety, and the work of Ed Clark and Doll is a good start for that, and also Agar could be used for that. And we want to optimize these algorithms to overcome the time overhead. And the simple idea would be to parallelize, for example, the queries, the many queries that L star is making could be done in parallel, and to perform more experiments. Okay, and this concludes my talk. Sorry, I'm a bit late.
Your conclusion about the effectiveness of learning-based assumed guarantee was somewhat negative, that it's not always a win-win situation. So I was wondering if that's because of the use of learning, or if the idea of compositional reasoning is fundamentally flawed. So I'm wondering if for these examples, you actually tried to construct manually the best possible assumptions and guarantees, and then saw if they were actually compact, or if they were so verbose that it's just not possible. So I mean, the thing is that I'm wondering if you had ignored the issue of full automation and just tried to construct the assumptions manually.
So what I
obtained compact assumptions.
No, I don't think so. I think so there are two answers. One is the assumptions with the alphabet refinement. Usually they are the minimal one. You can prove that, I think, I think they should be very close, and with the work of Sagar and Offer, they are the minimal ones possible from a language point of view that help you solve the verification problem. I agree that you still need some black magic to come up with the right decomposition and things like that, but at least with our work, it's still a push button, so you can just leave it overnight and crunch and find things. So at least you come up with A, but we didn't solve all the problems. And I don't think composition verification is flawed.
So the reason for the time blow was basically because of the number of iterations incurred in arriving at what you consider compact assumptions.
Yeah.
Okay.
So again, in some cases, if you make a guess of the good interface alphabet, which maybe sounds like black magic now, but if you have a concrete system and you understand a bit what it is, then of course you would have fewer iterations. But if you want to have everything automatic, you would need a lot of iterations to come up with it. And
So L star learns deterministic?
Yeah, minimal deterministic.
But that's overkill for this application.
Yeah, this is what people say, but in reality, we can discuss. In reality, this subset construction can prune a lot of states. And why is that? Because let's say if you have a path that leads to an error trace and another one that doesn't, it would also prune the state space that goes beyond that. So actually, the subset construction is useful in this kind of controller. It's a controller synthesis problem. So it's not that. So of course, in the worst case, it's expensive. But the fact that it goes from small automata to bigger ones, again, it's a nice property. And as I said, in practice, it can give you a good assumption. But as I said, it should be used with. So you should take this presentation Yeah, with a grain of salt. So it's not the solution to everything.
I mean, you have much more compact automata representation for assumption if you would allow non-determinism.
Yeah, but this is what we did with agar. Exactly, this is, so in agar, basically an assumption is an abstraction of the other component. But we can talk about, so in principle that one has a much better theoretical complexity, so in the worst case it converges to the M2, the whole M2, let's say the environment, while in the other one it will converge to the deterministic version of M2. But in practice it is not as simple as that, we found. So there are cases when one is better than the other. And we can speculate a bit. Tom Henziger also did a study in a slightly different setting where he looked at the interface synthesis using either learning or Seeger style techniques. And sometimes one is better than the other one. So.
Okay. Any more questions? No? Then let's thank our speaker. So Karina is here for the rest of the day.